Imagine Earth a few centuries from now. Space travel has become accessible, and we travel from planet to planet in spaceships like regular old taxi cabs. But sadly, right now we wouldn't have enough vacations in our entire lifetime to travel to the neighboring star system. To reach the nearest star, Alpha Centauri, which is 4.37 light-years away from Earth, we'd have to fly on today's rockets for over 50,000 years. If we want to get to one of the farthest known stars beyond the Milky Way called Icarus, we'd need 9 billion light-years. This means that even moving at the speed of light, we will never cross the Milky Way in a human lifetime. That's why NASA is working on types of engines that could potentially be faster than light. However, no matter how hard they try, scientists run into new challenges. In this video, along with our engineer, we'll test different types of engines to try and beat the speed of light. However, to do so, we'll have to find a way to bend the laws of physics. But just how catastrophic is this kind of experiment going to be for the universe? How close to the speed of light can we get? In 2017, Norwegian professor Espen Gardar Hogg came up with a new mathematical theory. He claimed that it's actually possible to create a spacecraft that, with the help of photons, can accelerate to 99.999% of the speed of light. A photon has no mass, its electric charge is zero, and it can only exist while traveling at the speed of light. Sounds perfect, doesn't it? But if we want to set a spacecraft in motion with photons, we need a new type of engine, one that can convert light into energy. Hogg claims that the best way to make this project a reality is a solar sail. So let's try building a sail that moves using light. To make 1 kilogram of matter reach the speed of light, we need a sail with an area of about 100,000 square meters that gives us an acceleration of roughly 1 meter per second. This means if our engineer weighs 70 kilograms, they'd have to design a square sail with sides longer than 2.5 kilometers. That's like 25 football fields laid end to end. And that's not even counting the weight of the spacecraft itself. But here's the good news, at least we don't have to worry about designing a fuel tank since we've got a free and endless source of energy, the sun. It's been burning for around 5 billion years already and will keep on burning for just as long. The beginning of our solar sail journey might be pretty sluggish, but the acceleration will be constant, and thanks to the sun, we can keep it going for years, even decades. In about 100 days of operation, the solar sail can reach a speed of around 14,000 kilometers per hour. After 3 years, its speed will hit 240,000 kilometers per hour, and then it would only take 5 years to arrive at Pluto, one of the most distant objects in the solar system. This idea of constant acceleration has prompted several research groups in recent years to test increasingly advanced prototypes of photon engines. In 2015, the Japan Aerospace Exploration Agency sent the LightSail 1 into orbit. Scientists managed to set up a solar sail with an area of 32 square meters on this small satellite. Within a month, the spacecraft, weighing 3,155 kilograms, had its speed increased by approximately 10 meters per second. Moreover, they were able to change its trajectory. This marked the first successful experiment with a solar sail, though it also shed light on its limitations, as the maneuverability of the design was quite low. To optimize the interaction of the photon engine with light particles, NASA is currently developing what they call a diffractive solar sail. The diffractive solar sailing project uses small optical gratings embedded in the thin sails to make better use of the sunlight. In the future, the photon engine will allow us to travel not just within the solar system, but also to the nearest star systems. However, there is a problem when it comes to interstellar journeys. The sunlight from the sun just won't cut it. The farther the sail is from it, the fewer photons it can capture. In hopes of solving this problem, an international project called Breakthrough Starshot plans to build 1,000 small solar sails, each weighing no more than 1 gram. These mini sails will require less light to accelerate. Meanwhile, back on Earth, researchers plan to construct an array of laser installations with a power of 100 gigawatts. Their beams will be directed at the mini sails, helping them speed up in space. The destination of this journey will be Proxima Centauri, the closest star to our Sun. Unfortunately, though, it'll take 30 years to accelerate these tiny photon sails to just 20% of the speed of light. Nevertheless, this will let us leave the solar system by 2030 and pass by Proxima Centauri around 2060. But let's imagine for a moment that our engineer managed to push the Starship with the photon sail to, let's say, 90% of the speed of light. What do you think awaits them? Well, of course, new challenges. Firstly, for someone moving at such a great speed, time will tick quite differently. Let's say our engineer embarks on a quick trip to Mars and back. It'll take them roughly 16 minutes and 40 seconds to reach the red planet and return to Earth. Now, here's where it gets interesting. For people back on Earth watching our journey to Mars, it will indeed be 16 minutes and 40 seconds, but for our engineer in the Starship, the round trip will only last 8 minutes and 20 seconds. This happens because, at such high speeds, there's a time dilation effect. The closer you get to the speed of light, the more noticeable it becomes. Besides, for our engineer, the space ahead of the ship will appear flattened into a blurry tunnel. After a while, they'll see nothing but darkness up ahead. The thing is, light waves simply won't catch up to them because they'll be moving at the same speed. In other words, there will be nothing but endless darkness before our engineer. So, in theory, scientists already know how to accelerate to the speed of light. But for now, the photon engine doesn't allow us to do that. You see, to achieve the necessary acceleration, we'd need a massive amount of materials to build the sail itself and an incredible amount of energy to power the lasers required to speed it up. To solve this problem, we'll have to create a more powerful engine that works on a different principle. Scientists have already come up with a theoretical plan for such a device. So, what's stopping us from turning it into reality? Theoretical physicists suggest using an antimatter propulsion system for space travel. It's a concept for a rocket engine that utilizes antimatter in combination with regular matter to generate energy for space flight. When these two types of matter react with each other, they can create an enormous amount of energy. It's 300 times more powerful than that of nuclear fusion, 1,000 times greater than that of nuclear decay, and 10 billion times greater than that of ordinary chemical reactions. But here's the rub: where do we get so much antimatter? After all, it's an extremely rare and complex substance to produce. Creating and storing it requires a colossal amount of energy. That's why engineers have been pondering the development of a hybrid engine to reduce the needed amount of antimatter. One concept of this kind was developed back in 1992 at the University of Pennsylvania, and they called it the antimatter-catalyzed microfusion drive. Its operation revolved around a fuel capsule containing deuterium, tritium, and uranium-238. This capsule was fired into a reactor chamber where it was first bombarded with ions and then hit with an antiproton beam. When interacting with the antiprotons, part of the matter in the capsule is annihilated. This produces enough energy to trigger the decay of uranium-238, which in turn initiates the fusion reaction with dumb and tritium. This energy powers big electromagnets that heat the plasma. Then, magnetic fields direct the plasma flow and shoot it out of the nozzle, creating thrust and setting the spacecraft in motion. The advantage of this system is that it needs relatively little antimatter for space travel. For example, to reach Pluto, you'd only need 100 grams of antimatter. That may sound like a very small amount, but not when it comes to antimatter. The point is, scientists produce it using particle accelerators capable of generating tens of millions of antiprotons per minute. That sounds convincing until you realize that at that rate, it would take tens of billions of years to produce just 1 gram of antimatter. Have you heard of antimatter referred to as the most expensive substance on Earth? It's true. 1 gram of it can cost hundreds or even thousands of trillions of dollars. And it's not just about creating antiparticles, you also need to figure out a way to store them since antimatter annihilates upon contact with matter. We clearly can't just put it in a container and call it a day. That's when we need special electromagnetic traps like, for instance, Penning traps. These devices, using magnetic fields in a high vacuum and at low temperature, can hold on to antimatter. Currently, portable traps are being developed, and they may later let scientists move the substance to other labs. One such mechanism is being developed at the European Organization for Nuclear Research, but at the moment, it's almost 2 meters long and weighs a ton. Assuming our engineer has enough antimatter, how safe would it be to travel on a starship equipped with an engine like that? Let's say our engineer accelerated the ship beyond the speed of light and is traveling in space without consequences for their body. But don't celebrate just yet, because when trying to stop the ship, our engineer could be killed by radiation. Imagine a photon peacefully cruising through the universe when suddenly our antimatter-powered spacecraft catches up with it. The photon will get stuck right at the front edge of the ship, and when the rocket stops at its destination, all those stuck particles on the front edge will simultaneously release an enormous amount of energy. There will be enough to wipe out not only the ship and its crew, but entire planets. Theoretically, the disaster can be avoided if we slow down a bit before reaching the destination and gradually reduce speed. But even with this approach, there will be intense photon radiation around the ship. Italian physicist Stefano Faini from the Italian International School of Advanced Studies and his colleagues explored this problem back in 2009. They found that the thermal flux from the photons directed towards the ship and its crew would be equivalent to a temperature not seen since the Big Bang, 10 to the power of 32 Kelvin, or something like 142 million degrees Celsius. So, one journey at the speed of light could endanger entire planets. On top of that, physicists say that a flight on a ship that moves faster than light could destroy the entire universe. How can an antimatter engine destroy the entire universe? In 1994, Mexican physicist Miguel Alcubierre developed a warp drive model. It was a theoretical mechanism for traveling at speeds exceeding the speed of light. The main idea of the warp drive is to bend spacetime around the ship in such a way that it's not the starship itself that moves through space, but rather the space moves around it. This means the spaceship won't violate the laws of physics that prevent objects with mass from accelerating to the speed of light. In essence, the ship will stay put. Space, on the other hand, is not bound by this law, so it can move at any speed. But here's the catch. Initial calculations showed that creating a warp bubble would require all the energy that exists in the entire universe. Besides, scientists are concerned that such a bubble could become unstable, especially when entering and exiting warp mode, potentially collapsing along with the ship. But let's assume our engineer managed to build an Alcubierre drive and set off into space faster than the speed of light. And let's assume they even avoided damaging the bubble and successfully regulated their speed to prevent a catastrophic stop. However, there's a problem that's nearly impossible to overcome: paradoxes. Alcubierre himself acknowledges that his drive is essentially a time machine. After all, any method that enables faster-than-light travel also allows time travel. The point is, the warp drive can create closed time-like curves. This means the ship can return to the same point, but at a different time. When our starship goes on a journey, space-time around it compresses. By speeding faster than light, we might end up in a space-time tunnel that throws us thousands of years into the past. This can have truly catastrophic consequences. We're talking about the so-called butterfly effect. The movie called The Sound of Thunder vividly shows the dangers of time traveling and how the accidental killing of a single Mesothenia butterfly can alter the course of evolution. In any case, to create a superluminal engine without destroying the universe, we'd have to break the fundamental laws of physics. But is that even possible? In 1999, British engineer Roger Shorter claimed he knew how to outsmart physics. He developed the M drive, a rocket model that, according to him, could produce thrust without expelling exhaust. The M drive is a hollow structure with powerful electromagnets inside. According to scientists, electromagnetic radiation bounces around inside the rocket. It travels from the magnets throughout the cavity of the device, and when the radiation accumulates at the narrowest part of the structure, it creates thrust in the engine. In 2016, a team from NASA's Eagle Works laboratories tried to verify if the M drive idea worked. The scientists claimed they managed to measure thrust. It was a true revolution in the world of physics. However, a team from Dresden Technical University, led by Professor Martin Tajmar, remained skeptical of the experiment's results and decided to try and replicate it. And they couldn't measure any thrust. The thing is, it was absent during the original EagleWorks experiment as well. The phenomenon detected by NASA scientists was a thermal effect. The sensor was simply reacting to the engine's heating. And if our engineer built a ship with such an engine, it wouldn't be able to move in space at all, let alone at some high speed. So, in the case of the M drive, scientists couldn't outsmart the laws of physics. But that's unlikely to stop them. Any space journey beyond the boundaries of the solar system inevitably involves breaking the speed of light. But at the same time, according to Einstein's theory of relativity, that's impossible. The main limitation of our abilities is that as an object's speed increases, its mass. As an object's speed increases, its mass also increases and is bound to approach infinity when it reaches the speed of light. Basically speaking, Einstein concluded that the speed of light is the maximum achievable speed in the universe. But modern scientists have come up with ways to potentially bypass the laws of physics and outpace light without actually exceeding it. They suggest creating a space-time tunnel. Let's imagine space-time as a grid. This fabric of space-time gets warped by the gravitational pull of objects. The deformed space-time creates something like tunnels, allowing you to take a shortcut between 2 points, known as wormholes. Physicists propose using these wormholes for interstellar travel. Despite the pessimism of some scientists who say that such wormholes could only form at the birth of the universe, others suggest looking for them near supermassive black holes. However, this option is highly risky. Anything that enters a wormhole gets accelerated almost to the speed of light, making any particles inside extremely dangerous for humans. It turns out that even if we manage to build a warp-drive starship right now, we might end up destroying the universe. Our attempts to bypass the laws of physics to avoid the end of the world might result in destroying ourselves. So, the question arises, is it even worth trying to outpace light? When we press harder on the gas pedal in a car, we go faster. A car has a maximum speed, but we can accelerate even more. For instance, fighter jets can move faster than the speed of sound. However, acceleration has its limits. No matter how hard we try, we can't go faster than 300,000 kilometers per second. To break through the speed barrier, we'd need an endless supply of energy, which unfortunately, we don't have yet. But it's not all doom and gloom. Scientists have uncovered the unknown before, like radio waves and radioactivity, so it's entirely possible that a new discovery will change everything. In your opinion, how many years will it take for scientists to invent a faster-than-light engine, or will intergalactic travel forever remain just a source of inspiration for sci-fi directors?